Hello again. Good morning, good afternoon, good evening, depending upon when you are watching this video lesson. Today we want to talk about random variables and probability distributions, which is sort of the title of the next section in our textbook. A random variable is a convenient way to describe the outcomes of a probability experiment. As an example, we might roll a die, six-sided cube. Number of spots on the top would be 1 through 6, and we might let x equal the number of spots on top. Then x is a random variable. Now, it's useful to use for random variables letters like X, Y, Z, W. Nothing says we have to do that, but it's custom. So you'll get used to seeing X as a random variable and Y as a random variable. Now, if we've defined the random variables, we can talk about events or outcomes when we roll this die. Maybe be like x equal 3. Well, that's an outcome. You roll the die and you get 3 spots on the top. And then since that's an outcome, we can also talk about the probability of x equal 3. And using the classical definition of probability, that would be 1 upon 6. So that's kind of the idea of a random variable. Notice that a random variable can be discrete, as this one is, or it could be continuous. Like we might select a student, and that would be select a student at random from some collection of students, maybe TLU students, and we could let y equal the height of the student selected, measured in inches. Well, now this random variable x was discrete because it can only take on certain values. It could only take 1, 2, 3, 4, 5, or 6. But this y random variable can take on any values in an interval. And so how small can college students be? How tall can they be? Well, without arguing for the real details, we can set a range of maybe 45 inches to, let's see, I'm just picking these numbers, but 45 to 84. In that interval, we'd probably catch all or mostly all the college students for heights in inches. There's nothing in here that you can rule out a priori. There are lots of values that you can rule out a priori here on x. It's not going to be 3.5, but y could be equal to, y could be 73.296 inches. That's a could be. So that makes that a continuous random variable. Now let's notice something else about the x random variable. If I would make a tree diagram here for you and list down under x the values that x can take, and then come this way and put the probabilities that x takes these values. This one's very simple, called a uniform distribution, because all of these probabilities would be the same if we're rolling a single die. 1/6 and 1/6. This T diagram would be called a probability distribution. Now, what is a probability distribution? Consult your textbook for a better English, more complete definition, But basically, here's all it is. It's a random variable with the values the random variable can take, along with their probabilities. So we'd have to know what the random variable is, what values it can take on, and what those probabilities are. And I'm going to give you a second example of a bit more complicated situation here. So you might have to watch this twice, but I want you to think about this. I'm even going to change the color here to emphasize that we're doing something pretty new here. So I want to take a bag, and inside it I want to put 3 balls. A red one, a blue one, and a green one. And the experiment is just this. With your eyes closed, you reach in and you pick one of these balls. So you select one without looking. Still without looking, you announce the color. So you do all that blindfolded. You're going to reach into the bag, you're going to randomly select one of these balls, and you're going to announce, I have just selected a blue ball. And then we'll open our eyes and see if you're right or not. The outcomes would be correct or incorrect. Correct, you got the ball right, or incorrect. What's the probability that you would get this thing correct? If you're just reaching in and guessing, if you don't have any special extrasensory perception, then I would think that you would get the correct color 1/3 of the time and the incorrect color 2/3 of the time. So those would be the probabilities of the little atomic events, or the atomic outcomes. It's kind of the most basic thing that can happen when you run this experiment. Now let's repeat. Just say 5 times. You're going to repeat the experiment 5 times, and we're going to let y equal the number of times that you get this correct. Well, okay. Then what values would y take on? Y could be, I'm going to do this T-diagram style now, just because I think it'll save us a minute or two. Y could take the value 0, couldn't it? You could do this experiment 5 times and get it incorrect every time. Or y could be 1, or 2, or 3, or 4, or you could get it right every time. So y is a random variable. The more formal definition of random variable is that it's a mathematical function from the sample space of an experiment, the set of outcomes of an experiment, into the set of real numbers. And so it uses a number like 0 to describe some outcome of an experiment. 0 describes what outcome. You draw in, you put your hand in the bag, you pick a ball, announce what color it is. You do that 5 times and you get it wrong every time. That would be a y equals 0. Now we want to calculate the probability of these different outcomes for the random variable. And when we do that, we'll have completed this T-diagram and have something called a probability distribution. So let's come over here to kind of our scratch paper and think about some of these probabilities. Maybe let's just kind of start in the middle and think about the probability that y is equal to 3. What does that mean? That means that you run this experiment 5 times, you get it correct 3 times, and since there are only 2 outcomes, it's correct or incorrect, it must be 3 correct 2 incorrect. You must get it correct 3 times, incorrect twice. Now, I want the probability that that happens. So let's just keep thinking about what has to happen when we run this experiment. I'm going to select balls from the bag, with replacement, of course. I took that to be obvious. 5 times. 1, 2, 3, 4, 5. And let's just, for notation, let's say a 0 stands for incorrect, and a 1 stands for correct, and a 0, and a 1, and a 1. So this is one history of this experiment. I select 5 times from the bag. I guess the color incorrect on the first selection, correct on the second, incorrect, correct, correct. And so this is an x equal 3 outcome. It's not the only one, but it's an x equal 3 outcome. Another x equal 3 outcome would look like this, and another would look like that, and there are more. And we could do these by listing because there's not going to be all that many, but if we can get a general principle for counting these, we'd probably be better off. Now, before we get that general principle, let's think about one other thing. Let's just take this particular outcome. That is, we get incorrect guess, correct, incorrect, correct, correct. What's the probability that we do that? Let me say it this way and see if you recognize the addition, the multiplication rule that we learned last week. I have to do 5 things, and the first thing has to result in an incorrect guess. And, see if I can write a little tiny and in here. And the second outcome is a correct guess, and the third is incorrect, and the fourth is correct, and that's not a very good and the last is correct. And we learned last week that when we're putting things together with the connective and, we ask ourselves, are these outcomes independent? If I get a incorrect guess the first time I try this, does that change the probability that I'd get an incorrect guess the second time I try it? And with a little thought, I think you'll say, these are independent outcomes. I'm putting all the balls back into the bag every time, and so it's always an RBG, one of each bag. The bag doesn't change, and neither do these probabilities, 1/3, 2/3. So this would be a probability of 2/3 times, because they're independent events, and I want the and, times 1/3 times 2/3 times 1/3 times 1/3. I'm going to write this way, and then if you're having trouble seeing that, you can think about it at your leisure, and you could ask me if you're still confused about it. 2/3 to the power 2, just using exponential notation, and that'd be a product. Now, this is a different outcome, but it still results in an x or y equal 3, doesn't it? What's the probability that this happens? It's 1/3 times 1/3 times 1/3 times 2/3 times 2/3, or exactly the same. It's 1/3 to the 3 times 2/3 squared. And this one would have the same probability. And in fact, there's a collection of outcomes that all make up y equal 3, and each individual has the same probability, being 1/3 cubed, 2/3 squared. Using the addition principle, I would need to add this to this to this to this in order to calculate the probability that y is equal to 3. But we know that rather than add all of these things up, if I just knew how many there were, I could just multiply by how many of these outcomes there are. So this is the problem of counting. How many ways can I put 1, 1, 1, that is 3 ones, and 2 zeros together in a sequence? And I think, again, with just a little bit of thought, there are 5 symbols here. There are 5 symbols, and I want to know how many ways I can pick 3 of these positions to contain ones. That would be 5, choose 3. Now, whenever I put my ones in, there's only one way to finish it. I've got to put zeros everywhere else, because if I'm going to have 3 successes here, I've got to have 2 failures, since I repeat this 5 times. So 5, choose 3 is how many of these elementary events I would have, sort of atomic events, and the probability of each would be 1/3. See, it takes 3 successes, and the probability of a success or a correct guess is 1/3. Got to do that 3 times, and you've got to get it incorrect, which has a probability of 2/3. You got to do that twice. So this number is equal to, and you know, we learned last week how to calculate these combinatorial numbers, and we know how to raise things to power. It will turn out that this is equal to 0.1645. And so that would be the probability that y is equal to 3 would be 0.1645. Let's do one more of these, and then I'll show you a shortcut here. What about this y equals 0? Y equals 0 would mean that I repeat the experiment 5 times and I get it incorrect every time. Incorrect every time. I think, following the same sort of thinking we did here, y equals 0 would have a probability. Well, I've got to pick no places to hold correct answers. 5, choose 0, and the probability of that number of correct answers would be 1/3 to the 0 and 2/3 to the 5, which is this would be 1. You could calculate that, but if you've got 5 things and pick none of them, how many ways can you do it? One way, don't pick any. 1/3 to the 0 is 1, and 2/3 to the 5th is 0.1317. 0.1317. Now we've still got 1, 2, 4, and 5 to calculate. They're calculated in a very similar fashion, but one can also use Minitab to do this computation. So let me show you how we can automate this, doing the calculation with Minitab. So we'll have to get Minitab activated. Well, that won't take long. I just found it, and I'll bring it over and make it big. And so here's Minitab. Now I've just started Minitab, and I've got a blank screen, and the only thing I've done is down here in the data entry section, I put a label X on C1 and a label P of X on C2. Now what we're going to do is to build a probability distribution for the experiment we've just been talking about. So we're just going to finish calculating the probability for X. I don't know why I call this X, because I called it Y earlier. Let's just change that. We'll make this Y, and then this would be P of Y. So much better. So we want to finish that T diagram. That means down the Y column I need 0, 1, 2, 3, 4, 5. It wouldn't take much to type those in, but I just want to show you that instead of typing those in, there's a pattern. A pattern in that data would be I would start with 0 and add 1 to get the next, and add 1 to get the next, and add 1 to get the next. So if we would come to, I'm going to size this so you can see everything. If I would come to calculate, make pattern data is an option. Now there's complicated patterns you can create with Minitab, but we just want a simple set of numbers. So I'll click that simple set of numbers, and I want to store this pattern in C1. So I would type in C1. Now since I've already named the column, you see I could just use the left-hand panel here and enter C1 or Y for where I want to store it. In any case, it's C1. Now what's the first value in this pattern data? It would be 0. And what's the last value that I want to create? 5. And in steps of 1. So I want to enter a pattern data, and the data is 0 through 5 in steps of 1. And the number of times to repeat each value is 1, and the number of times to repeat the sequence is 1. So this really is simple data. We'll say OK. And then, well, again, these would have been easy to type, but if I had a lot more data points, they wouldn't have been so easy to type, and so we've used make pattern data to put these values in. Now, let's get the probabilities. And we don't really even have to calculate these. This is fairly good stuff here. Let's go to calculate, and in calculate I can calculate a probability distribution. Now some probability distributions, you know, they're the T diagrams with the random variable on the left and the probabilities on the right, but some of them have names. And the one we're playing with here, where we're drawing these balls out of the bag and guessing what the color is, actually that probability distribution has got a name, and it's called a binomial probability distribution. So I'm going to select the binomial probability distribution, and now I'm going to answer a couple more questions. Do I want the probabilities of the individual points, or do I want the probabilities added up, cumulative? We'll come back to this later. But if we wanted the probability that y was less than or equal to 3, that would be cumulative. But what we're after are the answers to questions like y equal 3. So that's the probability, or the first of these 3 radio buttons. Now how many trials? Well, we're going to run 5 trials, and so we type a 5 into this box. And what's the event probability? That is just a way to ask, what's the probability of success here? And we reasoned that it would be a 1/3 probability that you would correctly identify the color of the ball if you draw without looking. So the event probability, this has to be in decimal. Minitab won't take 1 divided by 3, although your calculator probably will. Minitab won't. But as a decimal, that's 0.3333. And there are multiple ways to use this menu, but one way is to have an input column where we list the values of y, and that's what we have here. We created this input column. So the input column is going to be C1. That's where I have these values of y. And the output column, if I want to store this, I just list the column where I want to store the results. And that's going to be, we selected here a column C2 for my output storage, or P of y. So I can write C2 or P of y, or select it, it doesn't matter. Following input is not valid. Okay, let's see why. Because I'd already entered something in there. Just delete that. Select. I already had something in there. That's why it balked on that. Minitab keeps us honest when it can. If we say OK now, here's the result. And my gosh, it's very much like what we had calculated earlier by hand. Remember, we had found that 3 had a probability of 0.164. We wrote 1645. 164, looks like 1646 would have been the better rounding on that. And then we calculated 0 at 1317, and that looks like that's a pretty good rounding. But we had not calculated the probability y is equal to 1 or 3. Well, we did do 3. 1 or 2 or 4 or 5. They're done for us now. So this is a complete probability distribution for the random variable y, which is the number of successes if we draw the ball out of the bag and guess the color, and if we repeat that 5 times. And we could repeat the experiment 10 times or 20 times, and using the techniques that we've just learned, we could find the complete probability distribution. So we can ask questions like, would it be unusual for us to do this and to get 4 successes? Well, let's say 3. Let's say 3 successes first, because we calculated 3 earlier. So would y equal 3 be unusual? Well, the probability of y equal to 3 is 0.1645, so this is not unusual. So if you want to prove that you can do this because your fingers can see colors, if you run the experiment and you get exactly 3 successes, you've not really proved your claim, because that's not very unusual. A person with no ability would be able to repeat that result, y equal 3, 16% of the time. That's not very unusual. Now, what if you were able to have 4 successes? Well, we can see here the probability of y equal 4 is 0.0411. So the probability that y equal 4 is 0.0411, and that is less than 0.05. So we would say this is unusual. Getting 4 correct, that's kind of unusual because it has a small probability. Okay, more about that in the near future, but we've gone almost half an hour, so that's enough for this video. Thank you very much for being here. You may want to watch this twice, and you certainly want to keep up with your readings in the textbook. Ask me if you have questions or drop by office hours. You have a good day.